Okay, today we are going to problem 8, 15, and 19 of chapter 6. A dielectric sphere of dielectric constant epsilon and radius a is located at the origin. There is a uniform applied dielectric field E0 in the x direction. The sphere rotates with an angular velocity omega about the z-axis. Show that there is a magnetic field will be like this. And you recall the polarization from equation 4.757 will be like this, and our bound volume and surface charge density will be like this with these two formula. Our bound charge is 0 and surface charge will be like this. And the sphere is rotating, so our bound charge will give our bound current, surface current here. Our surface charge will give us surface current here. And our magnetic dipole will be like this. And so our magnetic surface charge density will have a relation here like this, and expand these two. This one will give us omega cosine theta, and this one will give us this one from the polarization here. Okay. And finally, will be like this. And next, if we want to calculate the magnetic field, then we need to integral over the surface contributed from our surface charge density, and it will be like this. And next, we use some tricks to change this one into spherical harmonics and expand 1 over r in spherical coordinates. And the opposite, this one will expand in spherical harmonics will be like this, and 1 over r expand into spherical coordinates. And the answer, and next we use the orthogonal relations for spherical harmonics. And finally, we will get the answer here. So we finish the integral inside the brackets, okay? And we keep sorting our field here, keep sorting our potential here. So finally, we will get the answer here like this. It's the same as this one. Okay. And next, problem 15. If a conductor of semiconductor has current flowing in it because of an applied electric field and a transverse magnetic field is applied, there develops a component of electric field in the direction of orthogonal to both the applied electric field and the magnetic field, resulting in a voltage difference between the sides of the conductor This phenomenon is known as the Hall effect. And part A, use the known properties of electromagnetic field under rotations and spatial reflections and the assumption of the Taylor series expansions around zero magnetic field strength to show that for an isotropic medium, the generalization of Ohm's law correct to second order in the magnetic field must have the form like this. And the Hall effect describes an electric field linear in the current density J up to a certain order in H field. Here, the maximum order H is specified to be 2, thus forming all quantities that look like vectors. The electric field could be of the form like this and a turn proportional to H cross and brackets H cross J is not needed because such a turn would be a linear combination of the last two terms of the above. Now, to see which terms are in principle possible, we check the transformation behavior of the terms. And we can check from the table 6.1 parity upon spatial inversion. E field is odd, so the A is allowed because J is odd, and B for the ABCD are all allowed. Okay, so all terms are allowed under spatial inversions. The labeling of the constants yields the equation in the question. Okay. A, B, C, D are all survives. And for part B, what about the requirements of the time reversal invariance? And our E field is time even order. So our A is not allowed because our current is time odd, and B is allowed, C is not, and D is not. And finally, only the usual B term is allowed under the time reversal here. And for 19, part A, apply space inversion to the monopole vector potential of problem 18 and show that the vector potential will be like this and show explicitly that its curl gives the magnetic field of a magnetic monopole. Expect perhaps at theta equals to 0. The magnetic field being a two-form or shift or press Bristol vector is even under parity and therefore G mapping to G, changing theta into pi substrate theta. Under parity in our expressions derived in problem 18, we see trivially that our vector potential will be like this, and do the integration, and we'll get the answer here and change into potential function. And next, verifying that this is indeed a monopole field, we have the B field. We calculate our B field like this, and we will find that there is no dipole no dipole here, so this is only contributed by the monopole. Okay, from the B field, we can check the dipole is 0, and the spare positive with the and because we have the cosecant and the cotangent function here, so it was diverge at 0 equals to at theta equals to 0 because it's cotangent. So, and for part B, show that the difference delta A can be expressed as the gradient of a scalar function, indicating that the original and space inverted vector potentials differ by a gauge transformation, and we can just direct calculate our difference A here, and the value will be like X, and recording that the gradient of a scalar field sigma in spherical coordinates has the 5 components given by this one, and finally, and so that our scalar field will be like this. And then the divergent and the gradient sigma equals to delta A as discerned here. And for part C, interpret the gauge function in terms of figure 9. And following the discussion from the context before the figure 9, we will see that we have the gauge transformation A mapping to A prime equals to A substrate G divided by 2 pi r sine theta here, and this one can be sorted into G divided by 4 pi times gradient sigma c here, and we can know we can know that our function will be like -2 phi here from the transformation directly. And finally, we finish the chapter 6 here.